already said in the chat, feel free to interrupt me. It is my honor to receive your comments and questions, your thumbs up or down. So we are here for, well, exchanging in a scientific manner. And this course is, well, an introduction to climate time series analysis, which I have taught many times before via my company, which is called Climate Risk Analysis, which is a small and medium-sized enterprise in Germany. And I had the luck to meet Biljana, who invited me to join the proposal, and the proposal got excellent marks. So I'm very happy that I can collaborate with her and the other partners in this project. So in the course I teach here, I usually say, well, you can't really do statistics and climate data analysis without equations. So we need equations, but these are things of beauty. They help us to communicate in a very efficient manner. And here's a very simple equation. The course, the C, comprises lectures, L, and tutorials. So I will give lectures, I speak, and then I will do some exercises, and you can either just sit down and relax and watch me, or you try to do it yourself. I brought with me some software tools for, well, doing the calculations. The slides are available as PDF, and I also put a part of the book into. So this is the book. The book is called Climate Time Series Analysis. The second edition was published in 2014 at Springer, and it has over 450 pages, and I put, so it's a commercial product, you have to buy it, and unfortunately it's rather expensive, I beg your pardon. Anyhow, I put a copy for you into the reading material, and this has already, I think, 150 pages, including the full references. So in these slides, on the bottom of each page, or of many pages, there are the orange fields, which contain the references to the books, so you are able to locate it directly yourself. So let me now proceed. And we study climate, different scales regarding space and time. We come from different study areas. I myself come from environmental physics. I did a PhD in geology, and then I studied, or I was a postdoc in statistics, so mathematics. But I always look onto the climate. And there are other colleagues out there working in geography or geology, chemistry, and so on. We have a united interest. We are interested in the climate. And we want to understand climate in a quantitative manner, numbers. Why? Well, this allows us to formulate harder hypotheses. We are more quantitative. We speak not about is there an effect, but how large is the effect. And we do this in dependence on time. So we have some time series. And we do analyze these time series. So this is a concept from statistical science. So statistics is not just making histograms or plots. It is a full scientific field with breakthroughs and different approaches, also within internal fights. And it's very important. It's a science of data. And it's important to speak that statistical language to a certain degree. And the computer is just a bloody machine. It helps me to implement the concept. So I can put in and I can calculate what I'm interested in. And no sweat, don't worry. I'll walk you through these formulas. I try to capture for you the essence of a formula. What's the idea behind the formula? And then we see the numbers. So you see my approach, how I approach the formulas. So the book has a number of chapters, 9 in total, and a course which I usually teach here runs for 4.5 days. So it's quite a number and an intense week for participants. and I don't expect that I'm able to deliver everything in this day. So I try to give you an introduction. What is a time series? Data, type, and measurements, and some examples. And then the major thing I want to approach is a regression, or the first part of regression, which is contained in chapter 4. In regression, we speak about trends, long-term deterministic signals contained in climate time series. For example, the rise of global temperature since 1850 or so. So we want to quantify this. And I want to be able to show you at least some methods for trend estimation. Because I think in the next talk on this senior researcher lecture, Rob Wilby will ask the question, what is a trend and what is not a trend? And I give you already a kind of mathematical approach, how to approach such questions. And while I'll walk you through to regression, I try to shortly make a dip into chapter 2, which is called Persistence Models, Memorizing Ability of Climate, and then also a bit into the hardcore statistics chapter number 3, Bootstrap Confidence Intervals. But I have to see how you are reacting, whether you are tired, whether you are interested, what is the time, and so I'm very open to see how far we proceed. So as I said and wrote, interrupt me, wave your hands and tell me, Manfred, could you repeat this for a chemist, or I don't understand this formula. Don't be shy. It's my pleasure to help you. So let us now go to the introduction. We speak about climate archives, variables, and dating, and then for the first time we speak a bit statistics, noise, and distribution, and then persistence, memory, warm today, well, okay, and likely warm tomorrow, but in 2 weeks, no one knows. So nature, climate memorizes over a certain time period, and we can quantify this, and we need to quantify this. And then, are there people working on paleoclimate, I mean the past 1,000 years or millions of years? Is there anyone who raises her or his hand? Okay. Because for those people, the time spacing is of relevance. But this seems not to be the case here. Therefore, I will be rather brief on spacing, and this also saves us time in the second chapter. So we are doing quite well. And finally, in the end, we look what can be typically done in such a course. What is our aim? What our target of the analysis? So let me start now with archives, and I follow the book. So this is figure 1.4. So in the orange field, this is a reference to the book. So if you are interested, then have a look on the book PDF you've got, and then you discover figure 1.4. So this is what is a climate time series? Well, actually, you see here 2 time series. On the horizontal axis is time, okay? And we see, let me see whether I can make these notes. I'm new to this system here, okay? So this stuff here, this is kiloyears. Kiloyears. This is 1,000 years, yeah? Okay, so we can look back in time over 420,000 years. And we see in the lower panel CO2. Well, CO2, the units are ppmv, parts per million by volume. And this is from an archive, from an ice core archive. And the ice core was drilled in the Antarctic island. And it is from the French-Russian station Vostok. And at the time the data were published, this was a major breakthrough, because we see that on longer time scales, over the past 420,000 years, CO2 changed strongly. And the upper panel, also from the Vostok ice core, is deuterium, which is a proxy, an indicator for temperature. And in tandem, we see the changes in CO2 and in temperature. So we learn that CO2 is related to these long-term temperature changes, to the ice ages. Okay, so these are in fact now 2 time series. And well, if you write a book, then you are in a good position, because then you can apply a consistent notation throughout the full book. And I invested some effort to be as consistent as I could be. So here we see the notation. A time series comprises 2 values for one data point. So first is T of I, this is a time, for example, 420,000 years, and X is the thing we measured, for example, 280 ppmv. I is the counter or the index, which runs from 1 to n, and n is the sample size, how many points you have. This is very important to know how many data points you have, because you will learn that later during this course. This determines how accurate your estimations are. And yeah, so this is important if you write papers or thesis or so. Give the sample size. Okay, this was a climate time series. And then second thing is what I call the climate equation. We have some climate variable x, for example, CO2, independence on time, cap T, and this equation is a decomposition. It tells us climate can be seen as a superposition of a trend component, x trend, and then we have perhaps some outliers or extremes, x out, and then what does not fit into this picture we call noise. So noise is a kind of abbreviation for something we don't know. And you see that I put in this variability function s of t. This means if s of t is large, then we have large variations around the trend. So if that, for example, is a trend, and this is time, and this is x, and then we have perhaps small variations around the trend. Here s would be small, and for example here we would have larger variations. Here s would be larger. Okay, so this climate equation honors the definition of climate in terms of not only the mean value, the trend, but also the variability, climate variability. So mathematically speaking, so x noise of t is a random process with a mean 0 and standard deviation unity. And the s of t is, well, the variability which scales this function. And in my view, in the past years or a few decades already, it pays to define climate also in terms of extremes, of the outliers. So it pays to invest another term into this equation, the outlier term. And this, perhaps Jana Silman from Cicero, I think her talk will be devoted to this outlier component. So let me continue and write the same equation in discrete time. So instead of x of t of I write x of I. So these are now the time points where we do have values. Okay, so first we had the notation, second we have the climate equation, and now the third thing we need is what statisticians usually do. They distinguish between 2 levels. One is the sample level, the time series, the small t of I, the small x of I. These are the actual numbers, 420 and some units ppmv. And the statisticians keep separate the cap x, the stochastic process. Okay, and this is the process level. We learn, statistics uses the time series, the sample, to learn about the data generating process. We are less interested in the in the actual numbers. We are interested in the system that generated the numbers in the climate. Okay, this can mean more concretely to estimate trend parameters, to quantify the probability of extremes, to detect cycles in the data and such things. So these are then technical aspects treated in the different chapters of my book. And there exist two basic settings where we can employ this. One is the univariate setting, just one variable x against time. And the second complex is the bivariate setting, two variables, x and y against time. But in this talk, we just stay with the univariate setting. So very basic setting to give you a good start into time series analysis. Okay, a short excursion into paleoclimatology. We look into the past with the help of natural archives, ice cores, lake sediment cores, or marine sediment cores. I myself did a PhD thesis on marine sediment cores on which oxygen isotope values were measured. And the sediment cores help you to look back in time over millions of years. So this is a way to get information about past climates. So and we can go back, well, till the age of the Earth. And anyone an idea? This is a first question of mine. How old is our Mother Earth? Anyone wants to try it? Biljana?
4.5 billion years.
Yes, good. 4.66 is the value I usually tell the students, but very good feeling. And okay, and we have the archives in the upper part of this figure, and in the lower part we have some dating tools, potassium over argon, or uranium over thorium, radiocarbon 14C, and other things. So these are tools my esteemed colleagues in paleoclimatology developed and adapt and improve. Some of them work on just one dating method, and other works on different archives. Okay, and you see that with climate modeling, you can evidently cover all the time scales, from the very short to the very long time scales. And once you've got a marine sediment core or an ice core, then you go to the lab and do some measurements. You make some geochemical measurements, or you measure CO2 in the air bubbles. We've seen this record. Or for my PhD thesis, I looked on 18O values. So this is we do not only have a 16O, but we also have a bit of 17O. And we also have a heavy oxygen, 18O. And the amount of how much 18O we have, this documents how much ice is on the globe. Okay, and this is measured on foraminiferal shells. So foraminifera are small animals, or they are on the boundary between animals and plants, and they build shells of calcium carbonate, and calcium carbonate is calcium. This is carbonate, and there's the oxygen, and this you put into the mass spectrometer, and then you can measure this. Okay, so, and my colleagues, other colleagues, they increase the accuracy of this proxy, because this is the good thing with proxies is you can look back in time, and the challenge is that a proxy sees many influences. So 18O sees not only ice volume, but also water temperature changes. So, and therefore it's often the question, what is ice volume? What is a temperature? So this is typical questions paleoclimatologists deal with. Okay, and this is again our series from Vostok to the right, and I just plotted for you these very long this long caption from the figure, because from the book, because I wanted to give the readers the full information about the archive, how long it is, and the definition of the delta notation, and the number of points here, and for CO2 we have 283, and so on. Then I alert readers that we can't see the current increase, and where is it here? So when I wrote the book, 2010, the atmosphere had about 389 ppmv. Now we are clearly in excess of 400, so this is kind of a dangerous experiment the humans are performing. Okay, so this is the way how I give the full information in the caption. Okay, let us talk a bit statistics, and usually when I show formulas, I try first to focus on the figures. So here the figure is a function f, independence on x. Okay, and this function should indicate what is the probability of observing a certain value. And it basically tells us probability is small here and small here, and in the middle it is high. Okay, mathematically speaking, we have to take the integral under the curve. The full curve integrates to unity 100%. And if you ask the question, what is the chance of observing x between a and a plus delta, then it is this shaded area. Shaded area under a curve, school mathematics, right? This is the integral. And this is the integral sign here, okay? So we integrate over this function f of x. This gives us a probability of observing a certain value. So probability density function, PDF. This is a fundamental concept for statistics. We may visualize how the PDF may look like for real data. And here we see histograms. In fact, we see 6 of those. And panel B, this one, is for Vostok CO2. And well, a histogram is the following. You just count how many values are in a certain size class, and how many, this you plot here then on this Y scale. And here on the horizontal, you take the values. Well, you will recognize perhaps that CO2 is positive, or at least greater or equal to 0, while here it can have negative values. So in fact, I use the residuals. I use the CO2 data, I removed the trend. I have to explain you how I did this. And what the resulting numbers are called residuals. And these are the numbers which represent the noise component of the climate equation. And this noise component we put into the histogram exercise. But we see that this curve looks rather nice. It is rather symmetric. It may be even a Gaussian of shape, okay? And it doesn't have outliers or so. So it's the assumption of Gaussian distribution may be fulfilled for this data set. But there exist other data sets. For example, that one here, this is Vostok deuterium, and it has a skewness. We have more power to the right, more values to the right, to the big values than to the left. And the arrows indicate perhaps we have even 2 modes, peaks of the PDF. It's not clear whether this is actual reality. Remember, we have only a limited amount of data corrupted with noise, measurement noise, and since it is paleo, proxy noise, and we make an inference, a guess of the truth based on this limited set of noisy data. Therefore, this is statistics. Our inference always has an uncertainty. And it is our task to quantify this uncertainty and to report this in our papers. Okay, the other 3 or 4 examples you find in figure 1.12, but usually or very often we observe a right skewness, more to the right than to the left. Okay, this is a mild right skewness here. So this is a kind of, I would say, climate property, a tendency for right skewness of the distribution of the noise component. Okay, next we deal with persistence or memory or serial dependence or autocovariance. There exist different mathematical names. But basically what is meant is the following. If it's warm today, I would bet it's also warm tomorrow and maybe the day after tomorrow. So nature remembers, okay, because it's a material, it is air or it is ocean water or something like this. It doesn't play a roulette at each second. Certainly there is a random factor, but there are also things that persist, that stay, and we can try to quantify that. And the autocovariance, this formula, helps us to do this. So what do we see here? X noise, this is a noise component at a certain time point t1. We multiply that by the same noise component at time point t2, and the time point should be unequal. So this symbol here is unequal. It's a mathematical symbol. And this here is the expectation. That means if you play these autocovariance, the product game over all possible outcomes of the PDF, what is the expectation that comes out? Okay? So this is the expectation operator. And the noise term, as I said, is assumed to have zero mean. Okay, now, warm today, warm tomorrow. That means X noise of T1, T1 is today, is positive, and X noise of T2, T2 is tomorrow, X noise tomorrow is also positive. Positive times positive is positive. Okay, then let us assume maybe 2 weeks before here we had a pretty cold weather, cooler than on average, then X noise of a day would have been negative, and on the next day it still would be negative. But negative times negative is positive. Okay, so we see that the memorizing ability of climates, this makes this autocovariance positive. Okay, we speak of persistence. So this is the expression I use in the book. And we can visualize persistence also on the paleo data, and or of course also on the measured data. And we look here on the residuals again, and again this here is Vostok CO2. And each, we see here 6 panels, and on each panel we plot here x of I minus 1, and here is x of I, okay? Warm today, warm tomorrow, or warm yesterday, warm today, this would make us sit somewhere here. Evidently, the time units here are kilo years, so it also, you see that also on longer time scales, there is memory. Okay, and cold yesterday, cold tomorrow would be here. So we have an orientation of the cloud of points along the one-to-one line, along the gray lines here. And you see that this applies also for Vostok delta D and also for the other records. And if you have a time series of, let us say, daily temperature at Novi Sad, you would well, you have to remove then the annual cycle, and then you would use the residuals, and you would make a Lagrange scatter plot, and you would observe a similar orientation of clouds, okay, along the one-to-one line. So there is memory. And okay, and we will later, I will try to do this in chapter 2, make a model for this memorizing ability. Then we introduce a parameter that quantifies how long we can remember. Let me proceed and lose a word on these residuals. So this is a climate equation, the top one, this is cap x, And yeah, okay. And we want to quantify this. This is the process level, and this is the sample level, the numbers. And we want to quantify the climate. That means we use the sample to determine the trend and the outliers and the variability. And once we have done this, then we are able to subtract the trend, we get rid of the outliers, and then we can also divide what comes out then by the estimated variability, S of I. Okay, details are then, that means more mathematical formulas are contained in chapters 3 and 4, but you see that you have to apply methods from later chapters, from the trend estimation. But I also think that you are able to proceed to trend estimation. So I will proceed now if I don't see someone getting nervous or fell asleep. Okay, I proceed. And now, briefly, since not many paleo people are here, the paleo people should be interested in the time spacing d of I, which is defined as the difference between two consecutive time points. Ti of I minus the preceding one, ti of I minus 1. And you see here, it may be a time dependence in the spacing. And the average over time is called the d bar, okay? This is a notation, and the paleo people can inspect the time spacing on their data. And here again is a Vostok CO2, okay? The past 420,000 years. And the time spacing in kilo years, in 1,000 years, is between, let us say, maybe 5 or 6,000 years, and well, this is 1,000 years, and maybe we are here at a few decades or so. Okay, and you see that it is anything but a constant. And we see also this one here in the deuterium. It's the same archive, and we see also a clear increase in the spacing towards the old ages, towards the bottom of the ice core. Evidently, it would be a bit much, but let me try. Has anyone an idea why do we have this trend toward larger spacing towards the bottom of the ice core?
Maybe the ice is compacted.
Exactly, very good. So we really did not make that beforehand. Biljana, excellent remark. Exactly. The ice core is you are sitting, so to say, at 3,600 meters below, and the ice is not a complete solid body. It has also properties of a liquid. Therefore, it flows, and you can model the flow, and the layers get compressed. Excellent. And you see that also the other. So this is from a marine core, and this is another ice core, and this is a speleotheme, and all of these archives, often employed, they exhibit uneven spacing. So the time spacing d of I is not a constant. And this is absolutely not the hobby horse of statisticians. Very often, they make their theory very often based on the assumption of even time spacing. But real life is often more complex. And also you working on measured data, there exist also situations where you have missing values, maybe during the Second World War or the First World War, or some information has been destroyed, or a measurement station has been abandoned for a while, or something like this. And it's, in my view, rather dangerous to kind of fill the gap and generate new data, because this brings you a step away from the original data. And therefore, in this course and in my research in general, I try to employ methods that can be directly applied to the unevenly spaced time series. Okay? And okay, as I said, missing values may be found in observations. If you have do computer modeling as our colleagues at Cicero in Norway, then you have the pleasure to have even spacing because you can write the output at an even time spacing. It's a good situation. But the other people working on documentary data, on proxy data, or also from the instrumental period on observations, we very often have the situation of uneven time spacing. Okay, so let me ignore this because we are not from Paleo. And we are now close to the finish of this introduction. So I was a bit fast, but we could ignore the Paleo stuff. Let me repeat. We have the climate equation. Climate comprises trend, outliers or extremes, and noise. And the noise contains the climate variability S of I. So these are the CapX. And we have the time series, our numbers, our hard-worked numbers, maybe done by a student in a lab or maybe downloaded from a website. Okay, these are the small t of I, small x of I. And we use that sample by means of time series analysis to learn about the data generating system, to learn about the climate. That means we want to estimate trend parameters. So this is what I will show in chapter 4. And Jana Silman perhaps is interested in the probability of extremes. And if you do spectrum estimation, then you are interested in cycles and so on. And this can be done in a univariate setting, just one variable, or in a bivariate. Evidently also in higher dimensions, but the course is on just these two settings. Let me see. Okay, this is now again on the problem of gap filling or unevenly spaced series. So is a zoom on the Vostok CO2 record from 30 to 80 kiloyears. And that the black values are the original data values. And you see, for example, that there's one value hidden here, a black one, and another there. But in between, there are no values. And you could be inclined to have an evenly spaced series at regular depth spacing, and you can then kind of connect these original data points by a curve, by an interpolation curve. For example, the blue one is a linear curve, and then you just read of the linear curve the numbers, the blue numbers. But there exist also other approaches, because the linear, well, it can be bands and it is not smooth, and if we make the assumption that nature doesn't make so big jumps, then we could perhaps prefer some smoother interpolation curve, and cubic spline is a technique to have a smoother curve. And you see that here the blue and the red agree very well, but here they do not agree. So interpolation is a step away from the original data, and it is also not clear how to interpolate. So this reinforces me to focus on powerful methods, powerful statistical methods, powerful data analytical methods, which are able to directly process the original unevenly spaced series. Okay. And then in the book, you see that I present a number of tables. So don't try to read the full caption. We see a number of entries here. So independence on sample size. We see some performance of for example, of a 95% confidence interval. So this should capture the true and prescribed value of 95%. But it's a Monte Carlo experiment. Therefore, we use artificial data. Therefore, we know what we put in. So these experiments, numerical experiments, computing-intensive experiments, they are used to test the methods, whether our estimation works, whether the trend is correctly estimated, whether the uncertainty measure for the estimate, a 95% confidence interval, for example, is indeed covering in 95% of the simulations the true and therefore known prescribed value. Okay, and once we applied once we tested that method successfully, then we are in a better position to apply it to our precious data. So the book deals also with this, and it shows very many of such experiments. Okay, introduction is close to being finished. I have a couple of slides on more data, and I would suggest I get your questions, immediate questions now. Then I will then make with many skips over the second chapter, persistence models, then the hardcore statistics chapter, and then I have to see how far we get. Perhaps then we need the lunch break and so on. I'm very flexible to accelerate and to expand and speak slowly, and I also listen. I'm pleased to listen what your questions are, and but be aware that this is the full course is usually for a full week, and I'm currently preparing the videos for what is called the climatrons for our project for EXtremeClimTwin. So these are videos which run, I think, for 12 or 13 hours in total. It's a huge exercise for me to do these online videos. So here I can make errors and no one tells, and it's okay, we are humans, but for videos I have to present a certain level, and therefore it takes a while. And but I'm pretty happy with the status, how it is. And you can watch and you have a look at my website for courses, whether for online courses or for offline courses. So here in the office I can accommodate for a number of people, and hopefully this COVID pandemic has an end better sooner than later, and I would be pleased to welcome you here in the office and teach you in person. Are there questions?
Also, you can use chat if you feel.
Yeah, well, okay, I will.
With it, you can use chat to write your questions, so it will be answered. Yes, thank you.
I see. Please keep your cameras on. It would be nice to have a group. So my camera is on, but Carly and Rob. Okay, no problem. I think you are still active, and I proceed without much ado. Okay? Yeah. Okay, then let me continue here. This is an example for extremes, the Elbe floods, not done in this course. Then we see, this will be done in the course, therefore let me spend a minute or so on this. This is, the archive is a marine sediment core from the equatorial eastern Pacific. And we see the past, well, the interval from 4,000 kiloyears or 4 million years back in time to 2,000 kiloyears, so from 4 to 2 million years ago. And we see on the vertical axis 18O, measured in a sediment core on the benthic forearms. And we know that already since we studied the table from the book, we see mainly ice volume changes and water temperature changes. And here, it's cold and much ice, and here it's warm. So paleoclimatologists usually plot their data in a manner such that to the top is nice and warm and mild, and to the bottom it's cold. And also these guys, they love to plot the age, okay? So in fact time runs this way. Okay. Anyhow, the physicists plotted the other way, but this should not get us nervous. Okay. And the thing is that in the course we see, well, in the lecture, what do we see here? We see many variations, this up and down, and these are in fact the ice ages. They are separated by roughly 100,000 years or maybe 41,000 years. But this is not what we are interested in the lecture. There we are interested in the long-term increase, and we will fit a model, such a model, to the data. And we want to quantify this change point and this change point here, and also the amplitude here. How much 18O came? How much ice came? What is the amplitude? What climate phenomenon do we see here? The answer, let me tell you here, it is the glaciation of the northern hemisphere. Okay, we had ice already on Greenland and Scandinavia in the Miocene, 14 or 10 million years ago. But these were, so to say, with bedrock, with land beneath. It's completely easier, in a sense, to build ice up when you have something on the bottom where you put the material on. And therefore, the ice sheets, they started to grow from northern Greenland and northern Canada and also Scandinavia. But then on the North Pole, we don't have land, we have water. And therefore, this ice grew, and it started to grow well. This was the idea behind this exercise. It started to grow at around 3.5 million years ago. So if you look for causes of climate changes, then you have to look somewhere here. What happened there? Tectonic changes and other things. So this, you see, why trend estimation, why the fitting of such a function is important. Because it allows you to learn about the causes. Okay? Okay, we have here, this is a radiocarbon record from tree rings for the Holocene. We see also here that, well, this is an indicator also of solar activity. And perhaps we had physics lectures in school or university, and there's expression of a solar constant. But in fact, this is not a constant. It varies. The amount of energy per time unit, per spatial unit, it varied in the past. And radiocarbon content in wood is a measure to visualize this, to measure this, to quantify this. Okay, and there's another, this is from a speleothem. Let me ignore this. This is a varf thickness. This is for the extremes, okay? So this is an extreme value here. So the task, this is chapter 6 of the book, is to detect the extremes and to quantify the rate of occurrence of extremes. How many of these extremes do we have? Because, well, this is a story in the book. We see hurricanes in the area of this lake. This was a lake near Boston, Massachusetts. Anyhow, sometimes a hurricane makes it into this area, and this lake hence can record such a hurricane. So the proxy idea is if a hurricane comes, it uproots trees and brings coarse material into the lake, and then we have a thick layer. Okay, and the task is then to quantify these the events and then to study the rate of occurrence. This is chapter 6 of the book. Let me proceed. This is now more the instrumental period you guys are more familiar with. Runoff, this is from climate models. Okay, this is not observed. And figure 1.10 from the book gives you the details. We see two panels here. So this is from a climate model. In a climate model, you can make wonderful experiments. The upper panel is for the experiment without humans. That means no greenhouse gas changes, no greenhouse gas enhanced hydrological cycle. Okay, and therefore, so without humans, and this is with humans. And here, so that the colleagues want to show that here the rate increases. And you see also here that the trend does not have to be a linear function. Here you could try to fit a linear model, but certainly here you would not fit a linear model. You would look for a change point. And you would use regression as a means to quantify the change point. And since we are dealing with statistics, we want to quantify the change point with error bars, okay? Because then we can speak statistics. We deal with the uncertainties. We take that fully into account. Okay, next one. This is again instrumental series, temperature anomalies on which we could make bivariate plots. Maybe we omit this. And this is then, well, runoff series from 3 stations on the on the Elbe. This is Dresden. And this is Deviation in the Czech Republic. And this is Barbie in Germany. And there you can study then the relation between both. Correlation. This is bivariate estimations. This is chapter 7 in the book. I beg your pardon. We don't have the time for this today. So you have a last chance to raise questions before I proceed to chapter 2. Marit? Okay, because you 4.567, where did you get the number for the age of the Earth?
Oh, no, it's just it's really easy to remember that one.
Okay.
But so it's a sort of
then we make the average, okay? Let me proceed now, okay? Well, how to proceed? I can make now the tutorial, but I think let me ignore to give you the exercise. I think you are senior researchers, you will understand what I will briefly walk you through with, and then we are with chapter 2. Okay, I will teach the same course tomorrow for the students, and there I will do this exercise. So because now this is here the tutorial, the T, okay. And then I would ask the people to open the data file in a text editor and check how many main values you have in a line. And what is the typical format? Rob will certainly agree with me that it is really important to deal from the beginning with the data quality in the format of the data files. Okay, so if you want to run software, my software from the course, then you have to transform your data into text or ASCII format. Since you are not a German, then you do not use a decimal comma. Hopefully you should use a decimal point, and please no 1000 comma, and also a carriage return line feed ends each line. Okay, you could try to do this on data. For example, on this file here, this contains this one here, then you have the data. So you have also, and you find it also on on the website for the book, the data and the software. Let me proceed. And we had this already. This stuff here, Biljana found out that this compaction we see here, okay? And now with the students, I would make an experiment on the bin width. Okay, this is a crucial parameter for making a histogram. You have the minimum here. Okay, this is given from the data. You have the maximum, but it is your choice how many bins to make in between. And here we see a number of 10 bins. But no one in the world prescribes you how many bins to take. You could, for example, use just 2 bins. It would look perhaps like this. You would hardly learn anything. And then in the tutorial, we make also very small bins. Then you have very many. And it's also difficult to learn from this. So evidently, somewhere in the middle is a good choice. And but there exist guidelines to do this in a quantitative manner. And let me show you a formula. This is a paper by Scott in 1979, cited in the book. And this is a quantitative approach to this problem of selecting the histogram bin width. This is called the smoothing problem. And in this context, we deal with it in density estimation. You lose the details if the bin width is too large, and you can't see any signal if the bin width is too small. And somewhere in the middle is a good choice. And this formula here is after Scott. And the n to the power of minus a third, this basically tells you if you have more data points, then you can make smaller bin width. And the rate is 1 over square root of 3. Okay? And then this is a factor. And this here is a sample standard deviation. Okay? You have also learned this in school or university. Take your data point, subtract the sample mean is given here, and then you square it. So it doesn't matter whether this is above or below the sample mean, and you sum this over all, so this is a summation sign, and then you divide, not by n, but by n minus 1, but in fact it doesn't matter so much. And then you take the square root, okay? So this expression here is units of x squared, but if you take here the square root, you have the units of x. So the sample standard deviation has the same units as x. And this is, for me, as a physicist, I like that, because it has the same units and I have an idea how big the variation is. Okay? And in fact, if the students do calculate this formula, then this is quite a good choice. Okay, this is exactly what Scott calculates. And also, if you employ advanced graphics software, I think they will come up with similar number of bins. Perhaps you have an Excel file or Excel software or R or something like this, and then you can discuss and calculate on this data file. What numbers you have. Okay, then scatter plot. Okay, this is for the students. You make 2 columns, x, and then and x plus at I plus 1, and so we have to shift it and then plot the points. No problem for you. Let me proceed. And Biljana, this is where I should praise Biljana. Biljana found the compaction in the Vostok I-score. Let me proceed. And okay, this is perhaps interesting to note, the relation between data and questions. Well, what do I mean with this? Well, if you have more data, you can ask more refined questions. You are in a position to answer more specific, more complex things. You can estimate more advanced stuff, change points and something like this. And evidently, if you have just a few data points, you should head for simpler questions. But it's an interplay between data and questions. Perhaps, for example, someone did some first measurements on a sediment core, but money was short and therefore only a handful of data points were generated and some interesting pattern emerged, but still it brought a paper, and then, okay, paper is submitted and accepted, and a new proposal is being written and new money comes in, and the same site is visited again and new data are taken, and you look on the same record but now with a higher resolution, and then you can ask more refined questions. The typical thing how science proceeds. Okay? Okay, hard and software. Computer is a machine. It helps us to calculate and to write and maps, to make such nice plots as I do for this course. Anyhow, you should know what tools to use. So this is what I typically advise the students. Doing your PhD, this is a good time when to think about what system and what tools to use. So I myself like, for example, the Windows machines. It's easy to install software, but if I have to do calculations and Monte Carlo, sometimes I switch then to Linux as the other environment. But I don't make a religion out of which systems you use. Some people like Windows, others like Apple. I don't care. Computing. I grew up with Fortran. It's an old-fashioned language, but still, if you want to do very fast calculations, there exist just 2 options, either C or C++ and Fortran. And also here, the pocket calculator is still important for me to carry, because I can calculate the numbers. And then occasionally I use Excel or some other spreadsheet software to visualize things and to make quick and dirty calculations, histograms or something like this. Also graphics, I tell the students that the reviewers of their papers, their professors, they are human beings. Humans like to see nice plots. So invest your time to make good plots. And therefore, you have also to think about what software you want to use for making convincing plots. So here, for example, this is a graphical tool, therefore I can't give you the full version. It has a demo version. I don't get any money by them. It's okay. This is something for visualization, because it's important for my software to work interactively, calculation, thinking, and then trying other parameters, and finally you proceed and get towards the bottom line and the final result. And this InDesign, this is a software by Adobe. Now there exist free versions on the net. It helps me to put PDFs in and without a loss of resolution, and so therefore I like it. And then I generate a PDF, and this is the thing I show here. Okay, so you have to think about what tools you use. Questions, Marit? No. Let me excuse me. Let me proceed. And there are no questions. I get a glass of bit of water, and then we proceed. Now it's 12 o'clock. Now I will move with you through this second chapter, and very many, I beg your pardon, slides I will skip. And we deal at length with this one, the first order autoregressive model, okay? This is the most important model, by far the most important model for describing the memorizing ability. Okay, and this is this model. Okay, we have an equation 2.1 from the book. In fact, it is two equations. The upper one, we have this epsilon, this here. What is this? This is a random process, and it has a normal distribution. The n stands for normal. And then it has a mean 0. So 0 is for mean, and 1 is for the standard deviation. So this here is a general way of expressing it. Okay? So that means the first point, I equals to 1, is a complete random draw from a Gaussian distribution which has mean 0 and a standard deviation unity. So this is a standard normal distribution. Okay? So this is the figure, and the mathematics would be that formula. Now we come to the memory. The second point, I equal to 2. What do we see here? We remember the preceding one, okay? And the strength, how well we remember, is quantified using this parameter A. Okay? This is a memory, and this is a innovation, okay? The random stuff that comes in. An innovation term with a mean 0 and variance 1 minus a squared. Okay? And you can remember, or you can recognize, if A is large, if A goes against 1, then this term here dominates. And if A is equal to 1, then all points are identical to because this is then 0, no innovation, no random component, and there is perfect memory, so to say. Of course, you do not observe this in nature. And A can also be negative, equal to -1, but in climate, usually you find hardly processes where A is negative. And so usually A is between 0 and 1, maybe it's 0.5. Depends on the resolution you have and the data you look at. Okay? So we can show, so this is now a bit of statistics. What is the mean of this expression? Well, let me skip this. The mean is 0 for all the points. And because we do this normalization here by 1 minus a squared, also the variance is unity for all. So maybe just the school mathematics. The variance of x noise of 2 is given by a squared times the variance of x noise of 1 plus, and then 1 minus a squared. And this one we know already, This is 1. Because this is here 1. Therefore, this is equal a squared plus 1 minus a squared, which is equal to 1. And this holds for all the points. Okay? Therefore, it is a process, this first order autoregressive process, which has variance unity for all time points. And the mean is 0 for all time points. So statisticians call this a strictly stationary process. Stationarity means properties do not change over time. Okay, and this is, don't get nervous about this formula, this is called the autocorrelation. This is the expectation of the product this times that, okay? And this is a normalization. And we know that this is 0, and this is unity. Therefore, we can get rid of this. Therefore, just this emerges, okay? And for this process here, it has such a autocorrelation function, such a memory function. H is the time lag, dimensionless number, 0, plus or minus 1, plus or minus 2, and so on. And this is a to the power of the absolute value of the time lag. Okay? That means at a time lag of 0, a to the power of 0 is by definition unity, and at a lag of 1 it has a value of a, and so on. And if we plot it, we get this curve. Okay? This is a fast decay of the autocorrelation function. The memory gets pretty soon lost. This is therefore the AR1 process, the first order autoregressive process, is called a short memory process. Okay, and this is a realization. So you use a random number generator, and then you put it in there, and then you get such a curve. Okay, you're still with me, good. Now is the first time that we speak inferential statistics. Okay? We want to know the true property, the true value of A given some noise data. So we have to guess it. And this is a recipe, this is called an estimation. And this is an estimator, A heads. The head reminds us that we are doing an estimation. And this is a recipe. Take the product of neighbor, okay, and then do the sum over all points, and then do a normalization. That means you divide by this. Okay, again we put in the residuals. So this is a recipe how to calculate A. So this is the only parameter we have to estimate, just A. A single parameter quantifies the memory. Okay, and then for statistical analysis, we do calculate what is called the white noise residual, so by that formula, and then this gives us these epsilon values, and we put this into tests of suitability of the AR1 model. And with Rob, I agree that the eye is a good way to judge things. It helps you to immediately spot errors in the data, and also to look how strong is the orientation of the cloud of points. For example, in this epsilon case, the eye would then, on the residuals, these are the blue dots in the scatter plot, likely not tell you there is memory. Okay, so this is an example on an artificial series, 200 data points, this is prescribed, and what we get is 0.717. Okay, this is the value of A hat. And the black points is the scatter plot for the data, and in blue is without the fitted residuals, okay? No memory. So that means the model is suitable. Well, no big surprise, it has to be suitable because I put it in. But in reality, with your data, you do not often know beforehand what memory model you have. You hope, and there are good reasons to believe that the AR1 model is a suitable model, but nevertheless, it's important to check also the fitted residuals. Okay, let me skip this, and Also skip that and we look on other models. This is a formulation for uneven time scales. Here you don't use A, you use tau, persistence time. It's a bit more inconvenient from a mathematical viewpoint, but it's basically very similar. So let me proceed now to other models, second order. Ignore everything. And this is now an AR2 model. We remember not only the immediate past, but also the second immediate. Therefore, we have to invest another parameter, A2. Okay, and this makes life more tricky. Two things are more difficult to estimate than one thing, and therefore we expect more difficulties. Okay, and there are also interesting phenomena you can observe on such models. So you call this model an AR2 model or AR2 process for even spacing. Yeah, and it has two parameters. And this is a plot in the A1, A2 plane of different properties. And if you are here in this dark shading region, then it appears, if you do a spectrum, that such a process has a peak in the spectrum. Okay, this would be chapter 5, a bit too far from here. But bear in mind that with AR2, you have another parameter, you can do more things. Of course, mathematicians like to generalize, and you can have many more. You have P parameters of the immediate past, and you have other noise components. These are called mixed models, mixed autoregressive moving average model. Various techniques exist for this. We notice that with great interest and proceed. There exist also other models with long memory, okay, where we see the AR1 model here. It is pretty fast at 0, but mathematically there are processes for which the memory does not decay so fast. The blue curve, long memory process, and this guy here, Mandelbrot, he was instrumental in developing such mathematical models. So this is also the Benoit Mandelbrot, a French guy who worked for IBM labs and long time. Very intelligent guy, very influential, but he had difficulties in the beginning in convincing the statisticians that such blue models really exist. Therefore, he published first in hydrological journals, and then after decades, all the statisticians noticed this. So this is also not so uncommon that the neighbor fields kind of help statistics to advance. Let me proceed, and we ignore this stuff. Let me also ignore that one. Let me mention this stuff here. Some people may claim that our AR1 model is a bit too simple, just one parameter to quantify everything in terms of memory. However, this is simple, yes, but we put complexity into the climate equation. So this can be nonlinear. And we have also the extremes in our definition. And we also have a variability that may be time dependent. That means we put the complexity into the other components of the climate equation. And till now, I'm quite happy with the analysis I did so far. And and the other colleagues, of course, are also adopting the climate equation. By the way, it is not an equation from first laws of physics. Climate is too complex, a system is too complex. This is a concept of mine and others as well, to describe what we see in the data. And then we make the description, and then we estimate the different things. Okay, then are there questions on the AR1 model? No. How should we proceed? You need a break?
Yeah, sorry, Manfred, there is one question. Alexander would like to ask something. Alexander, please unmute your microphone and speak.
Can you hear you?
Yeah.
First, before all, I would say special thanks to Professor Billion and their colleagues for the project, who invited me to be a part of this very important and interesting workshop. Thank you once again. And also, thank you, Professor Manfred, for a very valuable and interesting and very, very nice presentation and lectures. Thank you so much. You was talking about a little bit about Gaussian, I think, processes and about memories, I think. But can we, in this model, use martingales? You know what does mean martingales?
I don't know martingales, no.
Martingales, yeah.
I've heard that. I've heard this expression, but you caught me on the wrong foot. I would not be. I would fail the exam if I would have now to answer what that is. But are you referring to non-Gaussian shapes?
Non-Gaussian martingales, yes.
Well, if you can, at least there exist extensions of the AR1 model also for non-Gaussian shapes. This is no problem at all.
Okay, thank you so much.
Yeah, so maybe I go back a few slides. Here, you can also write here a skew distribution for this and this as well. It just has to satisfy mean zero and variability, standardization unity. And in fact, in the book, you find, for example, log normal AR1 processes. So thanks for the question.
Thank you so much once again.
So the next things that would come would be now the lecture, the tutorial for the persistence, and then would come the hardcore statistics chapter. And I wonder how I should proceed now. Biljana, can you give me a hint?
We have until 12:30, it's lecture time. Then we have 12:35 to 14 hours reading assignments. If everybody is up to, we can have a small break and then you can continue with the tutorial instead of the reading assignments, or you can suggest what we should, which chapter and which literature should be referred to for further learning these models and everything that you talked about just now. But if it's okay with you and everybody else, you can continue your lecture during these reading assignments and give us just an insight. What should we read maybe next week?
Well, it's good to hear this. I have the reading assignments at the end of when I finish chapter 4, because you know that I like my book, and you have the excerpt of the book. Certainly, I would recommend to have that book. But at the end of chapter 4, I also give you some papers, and I put it also on this X1 or drive, the online drive Minochair gave us. So this will be then rather specific reading material for you. So let me now just briefly walk through this tutorial and show you what you could do if you have a minute or so or an hour free time this or next week. So in the green boxes are the exercises, so the students would then calculate this stuff here. So you take then the product and the sum and this square and the sum, then you divide the numbers and you get the estimate, and they get hopefully the same. Then I ask a kind of a nasty question. Try to calculate the tau estimate. If you put in the numbers here, it's nasty because you can't solve this. If you have a certain number of data points, more than 2, you can't solve this. But it's not a problem. You have to apply numerical methods. And therefore, I coded this a couple of years ago into a software which is called tau-est, estimation of tau. And the software is contained here. Okay, so this is a software folder. And then there is a tau-est. This is one software you have. Okay, maybe I try. No, maybe I don't try it. You find it in the software folder. You have certainly access to. And the data file is then here. But in the tutorial, I often made a copy of that into the same folder so that life becomes easier. You will see how I do this when we do jointly the tutorial on the regression. Okay, then this is an explanation of the Tau S software. We just proceed, okay? It explains what you're doing and the type of plots. Let me proceed. Okay, this is interesting because now we deal with bias. Rob already mentioned this, but we now define what is a bias. At least this is our estimate, our estimator of A, and this is a recipe, the sum of the product of neighbors here, and then the sum of the squares. But the bias means the expectation of what you want to estimate, A hat, is unequal to, so this is again the unequal sign, is unequal to what you wish to estimate. This is evidently not, it does not sound so nice, but this is not uncommon in statistical science. And the thing is that you don't exactly know how large the bias is. You can only approximate it. So this means approximately equal to, okay? It's not an equal sign. And the bias is, for example, contained here. Minus 2 over n divided by A. That means if n is large, the bias gets smaller. Okay, this is, you just have one order here. And there exist more orders, higher orders of n, higher powers, by that formula by White. And I also, when I was at the postdoc in England, I also, well, I learned it the hard way. I programmed it on my machine, which I brought with me from Germany, and I found out that there is a bias. I couldn't understand why is there a bias, and then I found the literature, then I found that paper and that, and then I worked myself out a formula. Okay, so it's an interesting thing. And anyhow, you only can calculate it approximately. And the thing is as well, known mean, okay, but there is no climate goddess which tells you what is the true mean. You have to estimate it. Therefore, the mean is unknown. Therefore, these formulas are more of academic interest. And in reality, we deal with unknown mean. This is life. This is climatologists' life. Therefore, you have to subtract the sample means here from your estimator. And this estimator here, there, it's different from the one shown a few slides ago. Also that one has a bias, but this is the only formula, the Candle formula, I'm aware of, an approximation of the bias. And this, so therefore, what you want to estimate, well, it's nice, it's A, but this is a bias, okay? Again, it gets smaller at a rate of roughly 1 over sample size, 1 over n, and you can use that for bias correction. Okay, so this is what I do then. In the software, you can do this. And also in the course, in the next slides, I often show you a prime, a quantitative prime, for example, persistence time estimate, and prime means a bias corrected version. So this is a way how I express the bias corrected stuff in the book. This one we ignore, and some of the people, but not very many, have software to run model estimation. So there exists my software, Tau S, and there exists also another one, PAST, which you can freely download. But I think for that one, for the PAST, you have to have evenly spaced series. Let me proceed. Have a look at your faces.
Manfred, I'm sorry, but is it possible to make a short break? Only
good.
5 minutes, just to stretch our legs. I think it would be
Yeah,
useful for everybody.
I appreciate this as well.
Okay with that.
So sharply 5 minutes.
Sharply 5 minutes, yes. Okay. See you soon.
Again, this is chapter 3. It's important to understand because now we speak real statistics. We speak about error bars and other uncertainty measures. And it is a long chapter, and I will have again to skip things. And I would be pleased to answer your questions afterwards. You can send me an email, of course. And you find also hopefully time to study this in the book. So we now look first on error bars and confidence intervals and uncertainty measures, and then we speak about a powerful computational tool to obtain realistic error bars and uncertainty measures. Again, this is a climate which comprises trend, extremes, noise. We use the sample, small t, small x, to learn about the process. We want to quantify parameters and so. Now, statistics language, estimator. This is a recipe how to calculate what we are after, a parameter of our interest. If we do this, if we apply the recipe to the data and get a result, this is called an estimation. And the value of that we actually calculate, this is called the estimate, the numerical value. And the hat, we use this to denote an estimator or also an estimate. And we saw already, before the short break, that here we have an estimator, okay? The estimator for the AR1 parameter A. You can imagine there exist different models, different description of climate reality, different quantities after VR, and therefore different estimators. Also, there exist for the same quantity sometimes different estimators with different properties. And you can compare the performance of the estimators using Monte Carlo and other techniques. So this is now A hat, the estimator of the AR1 parameter A. And now, usually in the courses, I say this is the most important slide of this course. It is not designed very spectacularly. Anyhow, this is the essence for us, for applied statisticians or for climatologists who deal with data in a serious manner. This is the truth. Parameter theta, okay, the Greek symbol theta. We want to know theta in general. Theta can be anything. It can be the AR1 parameter, it can be a time change point, anything. This is what we want to know. But we have a sample, a small t, small x, and n is less than infinity. Despite we have millions or billions of euros or dollars, n is never infinite amount of data. And the data are influenced by observation errors. If you do paleo, then you have proxy errors. And also you guys dealing just with measurement data, Rob told us, measurement devices and measurement errors. This is ubiquitous. You find it everywhere. Also the climate modelers, excuse me, Marit, you deal with very sophisticated tools, but you also have to make some assumptions and you are not sure about all the different parameters you put in, the parameterizations and so. And therefore, to make it short, we have errors in our data and we have a limited amount of data. Therefore, our estimator, theta hat, never equals the truth. This is an inequality. We know this already. Okay, this is life. This is in all the applied sciences the case. We want to know the truth, but we have a limited amount of dirty data. This is a situation, but we are not lost. We can say how much typically how large is the deviation. Okay, then we speak about error bars or confidence intervals. What is an interval that contains with a certain probability this unknown value and so on. So this is statistical language. We make what is called a statistical inference, a guess of the climate truth based on a limited amount of dirty data. Now, the figure 3.1 illustrates basic properties of these inference. We see the PDF F of an estimator theta head. So this is a theta head scale. And for simplicity, I used a Gaussian PDF, but it could be also different types of PDFs. And we see different things. Here is the estimate, okay? And let us assume that someone told me what is the truth. Maybe if it's a Monte Carlo, then I would know the truth. This would be this, okay? And the difference is a bias. This is one thing, the bias. But we see also a certain width of the distribution of this, okay? And this is therefore described by the standard deviation of this distribution, which is called standard error, SE, for the estimator, SE index theta hat. And we speak of bias index theta hat. Okay, and the standard error is defined as a variance of this, square root of this, okay? And so these are two different aspects of the uncertainty. This here is a systematic error, and this is called a statistical error. Okay? You can imagine you shoot with a gun on a target and you kind of always hit to the right side. This would be the bias, and the scatter, how much this would be the statistical error. And you can combine both the bias and the standard error in this manner, which is called root mean squared error, RMSE, for theta hat. What is this? The error is this one, the deviation from the truth. The squared is here, okay? Then you play the game over the PDF, the expectation game, and then you have still units as of original theta, but squared, and as a physicist, I prefer the same units, therefore I take then the square root, the R, okay? This is the R. And this, it can be shown, it comprises a standard error and bias in this manner. Okay, so this is often a handy expression. No matter so much whether you report the bias or the root mean squared error, but it's important to report the uncertainty measure because this prevents you from making overstatements. If you have such thick error bars, then you can't make statements about such small changes. Okay, also shown here is an interval, a shaded area. Though this is 5%, this again is 5%. In the middle here is 90%. This is an interval for theta, okay? And we say with a certain probability, 1 minus 2 times alpha. In this case, alpha is 5%. Here is 5% as well. That means in this case, this would be 1 minus 2 times 5%, which is 95%. Okay, so this would be the confidence level for this confidence interval for the CI for theta hat. This is between the lower and the upper bound. Okay, so these are different uncertainty measures. The confidence interval, the bias, the standard error, the root mean squared error. And well, I will not show this. You can, for simple problems, calculate it. You can calculate the expectation. Okay, this is the estimation problem. You want to know mu. Therefore, we use here the estimator. We use a recipe sample mean. Okay, and this is the recipe. Take your values, sum them up, divide by their number. Okay, and if the data generating process is Gaussian white noise. Gaussian means here normal shape. Well, Gauss was a German mathematician, and therefore we in Germany call it also the Gaussian. Others call it the normal distribution. Anyhow, we know what we mean. We mean this curve here, this one. Okay, and we can calculate the expectation of that estimator. Okay, this would be then the expectation of mu hat would be the expectation of x bar. This would be then the expectation of that sum. This would be then the sum of the expectations plus x of 2 and so on. And we have each of that one has an expectation here of mu. So we have mu plus mu. So we have n, and this 1 over n. So anyhow, we have then, it's n times mu over n, which is mu. Okay, this is my dirty handwriting. And the same is now in formulas. The expectation is the same, okay? This is what we want to estimate, and this is the estimator. So it has a zero bias, it's the same, okay? We say the sample mean is an unbiased estimator of the mean for Gaussian white noise. This is a way how to express it. And we can also ask what is the variance of that estimator. It's a similar exercise, and we see that the variance decreases at a rate of 1 over n. Or if we take the square root of this, then we get the standard error, which decreases at a rate of 1 over square root of number of points. Okay? So that means, so in the tutorial, let me see whether I have the time tomorrow to ask the students. If you have 100 data points and you have a certain uncertainty, standard error of, let us say, 1 degree, and your boss wants that you cut it to a half, then you have to do 300 more. You have to have 400 values, because 400 is 4 times more than before, and the square root of 4 is 2. Then that means your error bar is divided by 2. 1 over square root of number of measurements. Okay, you can also answer what is the distribution of the estimator, and this is called a student's t-distribution. It looks rather similar as a Gaussian. Okay, and once we know the distribution, then we have the confidence intervals, and then we have everything, okay? And we can make a Monte Carlo test. Let me show the test for the mean estimator. So this is sample size. Data generating process is Gaussian, purely random or white noise. The prescribed values are mu equal to 1 and standard deviation equal to 2. And we look on confidence intervals of 95%, okay? And we calculate the confidence intervals using students' t-distribution. And this here, this gamma is called empirical coverage. That means the number of simulations where the confidence interval does include the value mu equal to 1 divided by the full number of simulations. And you see that we are very close to 95%. We are not exactly close. And the uncertainties here just come from the fact that we have a limited amount of samples, just 4,750,000. And that formula here tells you that you are accurate up to the 4th digit. Okay? So this is just numerical noise. That means everything is exact with that condition. That means we completely understand the problem. Simple data generating process, simple estimation problem. We can write down the PDF. We have everything. The confidence intervals are exact. Okay, and also this is the case for this for the standard deviation estimation. But now we put in a skew distribution, but we still calculate using students' t. That means we make the assumption that the data generating process is normal. So this distributional assumption is violated. And the effects are, we are completely off. Yeah, it should be 95%, but we are way off. And only if you have very many data points, 1,000 or so, then we are at coverage accuracies which are acceptable. Okay, that means the mean estimator and the accuracy of the student's t confidence interval applies. It makes the Gaussian assumption, and we see that in climate reality this is often violated. Ignore this, and therefore we need some tools to help us for the real world, for the climate world, and therefore we use what is called the Bootstrap. This is in general a method to construct approximately correct confidence intervals, and this is the idea. So you are still watching me, good. the idea of the Bootstrap. I explained then the different steps, but the first thing is you have your sample, and then in the computer, you just sit on your machine and do the programming and let it run. You generate new resamples. These are copies which represent new data sets. Okay, so this is one thing. The next thing is on each resample you reapply the estimation, the mean estimation or the trend estimation or something like this. This gives you one copy. Theta head, theta is what you're interested in, head is the estimate, and this asterisk, the star, is it indicates that it's being done on the resample. This is the first, the second, and you do this cap b times. And this is typically 2,000 or so. You get 2,000 copies, 2,000 replications, and this you use for calculating uncertainty measures, confidence intervals and error bars and so on. So this is the idea. So this is the one doing the resampling, and the two is to use the replications to construct the confidence intervals. Okay, and the resampling, let me show you this stuff here, the moving bob. The other things we omit. This is, here would be the ordinary Bootstrap. That means we resample randomly, point by point, with replacement from the original points, these x points, until we have again a sample of size n. Okay, that means sometimes you may, for example, this one, and then this, and this again, then this, and so. So we have a new sample of points. Some are sampled twice or 3 times, and some are missed. Okay. We make no assumption about the distribution. That means we preserve the shape because we resample from the data. So this is an idea behind this benchmark paper by the man behind the Bootstrap, by Brett Efron. But question, well, it's a more rhetorical question. Do we preserve the persistence? No, because we resample point by point. We lose the memory. There's memory between the neighbors, for example, and if you resample point by point, you lose this. Therefore, this is a problem. And this was immediately pointed out by statisticians after Efron, but we can adapt the Bootstrap, and this is a way how to adapt. It is called moving block Bootstrap, or MBB. Okay? And this is a length of a block, not just one block, but not just one block element, but L. Okay, this is L. And we resample a block, random blocks. Maybe first this block, we put it there. Then maybe some block there, we put it there, and so on. So we have a couple of blocks, and oops, sorry. And then we, from the last block, we discard the remainder that we are here at n points. Okay. So the idea is to preserve also the persistence, at least over the block length. Okay, so this is good. This is the Kunsch, Swiss statistician. And then, of course, there exist block length selectors. And we just know this formula. I use this in the book very often. This is the Karlstein formula. And, okay, it tells you if you have many points, you can use longer blocks. It also tells you if your memory is stronger, then you should also take longer blocks to capture their persistence. And the thing here, this is called equivalent autocorrelation coefficient. This is for the paleo people, the guys who have to estimate tau. And with the help of the average spacing, this is transformed into what I call the equivalent autocorrelation coefficient. Okay, so this transforms tau into A, and then you can use the Karlstein formula. That means you have a block length selector. And then the book then gives you the algorithms. Okay, that means a recipe how to treat your data. That means time series. We don't make assumptions on the time scale. We assume time scale is accurate. The residuals, that means data minus trend minus outliers divided by variability. This is now the equation for the residuals. And these are the numbers which represent the noise component. Therefore, we put those numbers into the MVP, okay? We apply it. We get now the resamples, which we plug in here. And then we get a new resample on which we estimate our stuff, our parameter. Okay, so this was how to do this, and now we look a bit on how to use the replications. The first thing you can imagine is, well, you have a bunch of 1, 2 cap B replications. The easiest would be to calculate, or not the easiest, one obvious option is to calculate the standard deviation over these replications, which is called the Bootstrap standard error, the usual formula. So to say, replication value minus replication average squared, so it doesn't matter whether one is larger than the other, then you do the summation, then a normalization, then you take the square root. Okay, this is called Bootstrap standard error, and this is called SE for theta hat, and which you plug in here and there, and then you get the confidence interval of type normal. So the assumption is that the distribution of the estimator is normal, which is often not a bad assumption, but sometimes it may be maybe better to replace against something else. Okay, this Z is called the percentage point of the normal distribution. Well, for example, if you want to have a 95% confidence interval, then you would take roughly plus or minus, then this would be not exactly 2, it would be 1.95, and so on. Okay, so this helps you. If you want to have maybe a 99% interval, then you would have to use here higher values. I forgot at the moment what value, and so on. So this is a normal confidence interval. Okay, let me skip this. Normal confidence interval is here. Students T looks rather similar. Okay, and in fact, if the number of data points and minus number of estimated parameters for mean estimation, this would be just 1, okay, number of parameters. But if you fit more complex models, you fit maybe 3 or 4 or 5. And this nu is the degrees of freedom, and if that is above 30 or so, which is usually fulfilled for sample sizes you guys treat with, maybe 100 or 1,000, then it's always easier to calculate students T. This is what I do in practice. I calculate students T, because then I'm on the safe side. The other thing I briefly want to mention is you can also size sort the replications. Yeah? The smallest one here, the largest one there, and in between are the others. And then you throw away maybe the smallest 5% and the largest 5%. In between would be then a 90% interval. Okay, this is what I draw here. This is called a percentile confidence interval. Okay, and then you can do a bias correction. Okay, let me skip this, and because I want to proceed to chapter 4. And therefore, excuse me also, this is advanced stuff. We don't need this for this lecture. And we also do not study this. We study later, chapter 4, a really interesting estimation. I beg your pardon. I only wish to mention you that applied statisticians and you guys in climatology, we do 2 things with inference. We want to know the climate truth. Yes, that means on one, we want to estimate a parameter theta, but 2, what we also do is we want to test a hypothesis, a statement about the climate. Maybe humans are contributing to climate change, yes or no, and we can test this, and then we do a hypothesis test. And then let me just give you an advice. This is old machinery, and they explained in the book. The assumption is, or you can also use a Bootstrap for this. Let me give you some guide. First, a p-value, if you happen to do a statistical test, then you should also give the full p-value, not just report whether it is below a certain threshold. And you should also formulate realistic competitors about describing climate reality. And then this here is what popped up in recent years more and more often times. This happens usually in the pharmaceutical industry. These guys are not interested in the truth. They are interested in making money. Therefore, they hide the non-successful hypothesis tests. But this is cheating, and you should not cheat. But way more interesting is this one. A confidence interval is more. It's more information than a mere hypothesis test. Consider the hypothesis. CO2 rise leads to temperature increase. Okay, you will get some data from a model or from observations, and you get a p-value of very, very, very small. Yeah, 0.0001, something like this. No big wonder. Everyone believes it. This is what physics tells us. It's way more informative to answer the question, how much warmer does it get? And so that means you do an estimator, okay, for the temperature change. And then you do a confidence interval for this. Then you can tell if we continue with our experiment, then it gets warmer by maybe 3.4 degrees with an uncertainty interval from 2.1 to 8.5 or something like this. This is not only whether there's an effect, but how large the effect is. So this is a general advice. Consider usage of confidence intervals, not just tests. Okay. You're still with me. It's great to see this. We are finished with a quick going through the chapter 3. And with great pleasure, I hear your comments and questions. And also Biljana, her advice, your advice on how to proceed.
Yes, Rob would like to ask something. Yes, Rob, please.
So, Manfred, I'm curious what your views are about the Bonferroni correction. I know you haven't covered it here, but when we're doing replicate tests against a given confidence interval, obviously if we do the test lots and lots of times, there's a high chance that we can get an apparently statistically significant result if we do enough tests. So do you recommend that sort of correction as a standard of high practice?
Yeah, well, it's good to have it, of course, because it seriously treats a problem. It recognizes a problem, and it is developed by statisticians. So much brain power went into this. Evidently, we deal with a problem of multiple testing. It depends a bit on what tests you are performing and what the data generating process is. If you are dealing with more complex tests, fingerprint tests where a high-dimensional climate model output goes into one single test statistic, and you don't know exactly what is the memory and the distribution of the data, and also the test statistic is constructed in a complex manner, it may be difficult to do an analytical correction as you described. I would feel better if such corrections would then be backed up by Monte Carlo evidence. You can do this. It's a lot of computing, evidently, but of course, we get faster and faster machines. My plea to the climate modelers is do not invest everything into increasing the resolution. Please do also more runs, that we are able to better assess the accuracy of the climate model output.
Okay, thank you.
Is it okay for you, Marit? Okay. Other? So I spoke now for 2 hours or so. I can, my voice is still okay. I can proceed now to chapter 4. I don't know exactly, we speak, you have me till 2 o'clock, is that correct?
Yes, until 2 we have lectures, and then on 4 practical.
Yeah, okay, yeah.
So you can use the time until 2 o'clock.
I think I will be able to deliver something you can digest before lunch as a kind of a starter. Then we have lunch from 2 to 4.
From 2 to 4 we have a coffee break and
Coffee
lunch,
break, yeah.
and we come back at 4.
Yeah, it's good. So let me, excuse me, I will continue speaking, and without a tutorial, the tutorial would then be in the afternoon after the coffee. Okay, then we go now at a more gentle speed through the next chapter. Not this one. Regression 1. Now we are in a position to speak statistics, the language of uncertainty. And now we have certain questions about the climate. And here in this chapter, chapter 4 in the book and chapter 4 of this lecture, we speak about the trend. And Rob as well likes such questions, so I hope that you get something from this lecture. First we start simple, of course, linear models, just fitting a straight line. But then it may be the case that also we want to fit nonlinear functions or something like this. And perhaps if there is time, then I deal also with another trend estimation, namely non-parametric regression or smoothing. But let me see, and let me see what you want when I'm there. So let us start simple, linear regression. Again, now we know this is a climate equation. Climate comprises trends, extremes, noise, and the noise is scaled by a variability S of I. And the small t, small x, we use to learn about the process. Okay? And now we focus on the trend. We ignore the outliers, and we look here on the variability and also on the trend. Okay? So this is therefore we deal with what these old guys, the Austrian, German, Russian meteorological school, end of 19th century, how they defined climate. And so we look on the trend and on the variability, climate variability and climate changes, okay? And you can either make a parametric model, so it's your freedom, you have the data, and it's your freedom what model to choose. With a linear model, you head for a simple description. A nonlinear model, then you can accommodate, for example, for complex changes, acceleration points, change points, jumps, and so. By the way, Rob, also you use such models to test for inhomogeneities in the data. So regression methods are very helpful for your research. I'm pretty sure. Well, of course, you employ this. But also non-parametric descriptions sometimes are powerful because they are not so restrictive in terms of parameters. You can also learn from applying such models. So let us the linear trend model. Okay? If you let me show you. If you remove these outliers and you assume that just here the variability and the trend, and if you do a linear model for this, beta 0 plus beta 1 times t of I, maybe I should use a smaller pen. Let me do this. Yeah, it's better. Okay. Then you directly enter this model. This is a linear model. It has two parameters, intercepts, beta 0, slope, beta 1. Okay, and we are after at the values of beta 0 and beta 1. Okay, and this can be achieved, this estimation, using different approaches. One approach is shown here. It is called weighted least squares, WLS. What is this? Data minus, this is the fit line, okay? At a certain time value, and then in the usual manner you square it, so it doesn't matter whether you are above or below the line. Then you do the sum, okay, and then this is a quantity which you want to minimize. That means you look for the values of beta 0 and beta 1 for which that sum is a minimum, because then this line is closest to the data in this least squares sense, okay? And then, maybe I use another color, why not? This is now the weighting. You divide here by S of I. That means you do a weighting. Why this? Well, there may exist data points for which S of I is smaller, less variable climate, or higher accurate measurements. And these points may better inform about the climate. They should deserve more power in the estimation. Therefore, we call this weighted least squares. Okay? So if we divide, so this is the rule, if we divide by something smaller, then this term gets heavier weight in the estimation. This is the idea behind weighting. Okay, so we have now a sum of squares. It depends on two parameters. So in school mathematics, you would take the derivatives. That means delta S as Q W of beta 0, beta 1 divided by delta beta 0 or beta 1, and this should be 0, okay? And this is, you have two equations, two unknowns, you can solve it, and these are the solutions. These are called the weighted least squares estimator of slope and of intercepts, okay? And you use this abbreviation, the cap W, which you easily get from your weights. Don't get nervous about these equations. This is just products and divisions and summation done in a nanosecond on your machine. No problem. Now you know at least what the computer does if you press the button of your linear regression package. It just calculates this stuff here. Okay. Now this is our model, but there exist also other approaches. One is called ordinary least squares, or OLS. That means you do not do weighting here, you just divide by 1. And that applies for the situation, well, if the variability is a constant or you don't know it. It's also possible to calculate then the OLS estimator. So sometimes in the paper you come across the OLS estimate for the temperature increase is and then so and so many degrees per decade or something like this. Now you know what is OLS, ordinary squares, no weighting. It's even easier to calculate than WLS. Okay, this is now shown on the example of modeled river runoff. So we have here an elaborated climate model from the Hadley Center. It's a couple of years old, so the paper is from 2005. The model is a bit older. Hence, we see two panels, the upper without humans, no greenhouse gas changes, and this one is with. Therefore, we have here greenhouse gas changes and the temperature rises over time, and the temperature via the Clausius-Clapeyron equation, the atmosphere can carry more water, and therefore the hydrological cycle is enhanced. And therefore the paper, this is by Wu et al. In 2005. I will show in the later. At least these guys wanted to convince us, and they want to quantify the effects of the humans on the hydrological cycle using this model. Okay, they find two slopes. Okay, so the upper one here, this is a straight line, and this is an estimate for this. Okay. And later in the nonlinear stuff we will study this one here, because I'm not so happy about these two lines. For example, one is why does it start here, the line, why not here, and such questions. We can do better, we will do this, but only in nonlinear regression. At the moment, let us stay for a short while with linear. Okay, then there's also the option to use another estimation approach, which is called generalized least squares, or GLS. Okay, this is now matrix notation. Don't get nervous. This is just now this is vectors and matrices, But you see easily that this is a parameter vector which comprises the two parameters, okay? And then these are your data, and these are your time values. And you put in the ones here, then you have the time metrics, and then you can calculate these. Easily done, nanosecond. And this is then the estimate, okay? This is again the parameter, the vector, okay? This is therefore beta hat is equal to beta 0 hat, beta 1 hat, okay? And yeah, then just my daughter's visiting me. I have no...
Du kannst nicht essen.
Nee, ich kann nicht essen.
Du kommst irgendwann?
Ich komme später rüber. Excuse me, my wife and my daughter just showed up and I have to tell them that they have to wait for me to lunch. Anyhow, this is now the covariance matrix elements, the V matrix, okay, which you find here. And these are the variabilities you need to know. This is a persistence time, estimated the hat, and the prime is bias correction, the Kendall formula. So you put this in, and then you have the V matrix, and then you have the estimates. And you calculate the residuals. The unweighted ones, those here, data minus fit. And then you divide by estimated variability, you get the weighted residuals, the R's. And you can do some theory if the true shape is Gaussian. And if the covariance matrix, the V matrix, is correctly estimated. And if, third if, the model is suitable, the linear model, then the confidence interval for intercepts and slope is given by this expression. So this is the student's T. Okay, okay, you need this standard error for this, which you get here. And for this, you need this matrix, you get there, and this is everything, you have it. That means you can calculate it. You can calculate the confidence intervals. Okay, so this is again what you are perhaps more advanced, the software package which delivers confidence intervals does calculate when you press the button. Okay, let us ignore this one. Because in reality, it's a bit more complex. If we know, this is a very heavy no, variability in persistence, either tau for uneven spacing or A for even spacing, that means if you know the V matrix, then the calculations are easy and straightforward estimation is done. However, no climate goddess, no one tells us what is the truth, we have to estimate. And this is, that means we have to proceed in, well, using more advanced approaches. Okay, we don't know variability and we don't know persistence. That means I will show you two things. One is a procedure named after Brace and Winston, and the other is we calculate via effective data size. Or maybe, let me, for the sake of brevity, we skip this, and I only show you effective data size. Okay? So I ignore this, and we calculate this way. This is a formula. This stuff here, we had this. I had this a second ago or a minute ago. This is the estimated variability, and you get this by data minus fits, summed, squared, summed, and then the square root. This is called the residual mean square, this MSE. Okay, this is a classical formula, a classical means without simulations, making assumptions, Gaussian assumptions, and doing some calculations. And now we introduce here for n, n mu primed. Prime means it is called effective data size. Effective data size regards the situation that we have memory among the data points. That means we don't have the same number of independent voices, so to say, but it is reduced. Okay? If I always say the same thing as my neighbor, and this applies for the full audience, then the number, then n prime would be n half, okay? And therefore it is reduced. And if I divide now by something smaller, this is a rule, then the thing gets larger, then this goes up, as it should. So the intervals get wider. This goes in the right direction, and we test this using a Monte Carlo. And this is then the result. Let me first show you. This is a number of simulations, and this is what I put in. Intercept is 2. And this is then the coverage for the intercepts, okay? This one here, gamma 1. This is sample size. This is nominal coverage, 95%. And then you can either ignore persistence, then you are here, but you are completely off. 82% or so, not 95. Your intervals are too small, too narrow, because you ignore persistence. And if we take persistence into account via this effective data size, this formula here, the intervals get wider, and then they capture the true value of 2. Well, in a very good manner. We are here at 95 or 94%. So it works very well, this approach. It works. Therefore, we can apply it, and therefore we get then these uncertainties, okay? Well, I get, more precisely, I get those here. This is what I got, 0.441, okay? If I calculate via effective sample size, and I also calculated it without effective data size, that means with original data size, then I get those numbers here, 0.356. These are, by the way, the same as what the authors reported. So I kind of caught the authors in making an error. They reported too small error bars. However, they were lucky because this estimate here, it is 0.102, and the uncertainty is 0.441. And even if you make the error, you get 0.356 as uncertainty, which is still 3.5 times larger than the estimate. So it is not a significant change. So it is no significant slope here. So we deal just with A. Okay? That means that they were on the lucky side. Okay. You are still here. Okay. Questions on the linear model? Because now we turn to nonlinear. And this would be for the remainder of this lecture. So this was more or less stuff you heard in, maybe not in school, but in mathematics lectures. If depends on what study you have and whether you have analysis and statistics. But in my view, this should belong to the education of climatologists. Now we deal with more advanced stuff, nonlinear functions. And well, we see here first a parabolic model, which is this curve here. However, the thing is that you could model this also with this term, and this is a linear term. That means it is not really a nonlinear term. So this would be a nonlinear function, such a curve, this saturation curve here. Yeah. So this exponential decay or increase. It has two parameters, beta 0 and beta 1. So it is more difficult to fit such a model. In general, now a general slide. You are in a high-dimensional space spanned by the different parameters. If you have a complex problem, you have many parameters, a very high-dimensional space. Maybe not just beta 0, beta 1, but maybe beta 2, beta 3, beta 4, and so on. And how to proceed, how to find the minimum. There are usually no analytical formulas for this, so you have to use, well, some numerical techniques, and you have also to take into account your background knowledge about the data generating system, about the climate. So perhaps you can start here with a well-found starting value in this space, and then you calculate the gradient of the sum of squares as is q, and then the gradient tells you, it is an arrow which goes in the direction of the steepest increase in that space. But of course you want to go in the other direction. Therefore you go into the negative gradient direction. And here you recalculate the parameters and the sum of squares and the gradient and so on. So you kind of move along in this space, and only if then the changes are small, you exit, then you are done. And small depends, well, it depends on the accuracy of the representation of numbers in your machine. Okay, so, well, 30-bit 2 computers and normal precision you have usually in the order of 8 digits. Therefore, you would use an epsilon of maybe, let us say, 10 to the power of -6 or something like this. You should not take -10, because then you would be requiring smaller. Then you actually can represent numbers on your machine. This would not be a good choice. So again, you can speak in terms of numerical methods. So it's a very interesting thing, numerical mathematics and nonlinear regression. But anyhow, let me proceed here with a more handy tool, which I developed end of the, well, I kind of worked with that already during my dissertation thesis in the 1990s, and then postdoc statistics, I worked on the Bootstrap and formulated the uncertainties. This is a model. It is called the ramp. It has 4 parameters: the change point times T1 and T2, and the levels x1 and x2. And it has a constant here, then it's constant there, and in between it's linear. Okay? So this is the figure, and the formula is that one here. And it serves as a model for climate transitions, okay? So if time runs, let us say in this manner, then we have one change point here, and then after a while, then it changes, and then it settles down and has a new value. So this is the idea behind the ramp. And of course, we want to fit the ramp to data. And we employ, as before, a weighted least squares criterion. So data minus fits, squared, summed, weighted, it should be a minimum. Okay, now the school mathematics does not help us. At least it does not help us for the sake of determining T1 and T2. It does help us for determining x1 and x2. This goes via taking the derivative for x1 and x2, okay, as before with the linear regression. But for the overall minimization, we have to find the suitable values of T1 and T2. And for that, I use a completely unelegant method. I search by brute force for T1 and T2. So T1, or the search values, is element of all the time points. Okay? And T2 as well. Okay? I try all combinations, and then I just take that solution which gives me the overall minimum value. And I found out that for sample sizes of maybe thousands or tens of thousands of values, this is still feasible thanks to modern computers. Okay, when I did my PhD 25 years or so ago, computers were admittedly not so fast, but with today's machines, we can do the brute force search. Okay. And this is then the example for the ramp, the Northern Hemisphere glaciation. And we looked therefore for the change point times, when did the Northern Hemisphere start to build up the ice? Here. Yeah, this is 3,700, and then it ended here. Okay, in between we had the increase. And I fitted a ramp in order to quantify from when to when. When was the change point? And how much, what is the amplitude? Because this, yeah, the amplitude in delta 18O, this is an amplitude in ice volume. And this then is an amplitude in sea level. Yeah, you know that people are discussing what happens if Greenland ice melts or Antarctica, and so it helps us to put into context, yeah, if you know the sea level change. Okay, but still now we don't have the error bars. We only have these estimates, and in the remainder I will show you how to calculate realistic error bars with the help of the Bootstrap. There are no classical formulas. Yeah, the gradient is not defined. You can't take the derivative of the sum of squares with respect to T1 or T2. The gradient is not defined. We are not lost. We can resort to Bootstrap resampling. So the task then is to give error bars for these estimates, okay, with the help of the Bootstrap. And this goes as follows. We calculate the unweighted residuals, the E's, okay? Data minus fit, shown here, okay? And then, okay, in the tutorial we make an exercise to do the weighting, and here I will just show you that if you do this, the variability here is a bit smaller, and here it's a bit larger variations in ice volume. And therefore, in the tutorial, we will learn to fit a model to the variability, to the S. And if we fit this, then we can divide by the variability. That means we divide by something smaller here. That means this gets inflated compared to that. So and therefore, the weighted residuals shown here, here it's roughly the same in size before and after. So this is the idea behind this weighting. So you kind of fit per eye a parametric model to the variability. This is the idea behind the weighting. Okay, and these are then the R's, and the R's are put into the Bootstrap because these represent the noise component. And we use block Bootstrap because we have the memory, so estimated using the persistence time estimation from chapter 2, and then therefore we take the fit curve, we add blocks of the residuals until we have the same sample size, and if we have this, then we have the resample to which we reapply the costly brute force search to estimate and get a replication, a new copy of the 4 parameters, and that we do a couple of times. We get 400 or 2000 copies for T1, for T2, for X1 and for X2, and for over those I show now the Bootstrap standard error. That means the standard deviation over the 400 copies. And these are the values here. Okay, now we are in a position, now we can, we know how big the uncertainties are. So we are here, the estimate would be at 3.7 plus or minus 166. Okay, so you could draw this one here, and here we would be at 2462 plus or minus 200, something like that. Okay. Of course, you can show the uncertainties also in the plot. Okay, so this would be the outcome. Okay, but as life is, you see here this the node. When I did the calculations, I used an older version of the software which employed another resampling approach, not the moving block Bootstrap, but what is called the stationary Bootstrap. It's a, in the stationary Bootstrap, the lengths are not constant. Only the average length is preset. But in reality, this is more for mathematicians. It's not really interesting. It's not, it has no all nearly negligible effects. You can ignore this. But this is just, I have to be honest, how I calculated the number. Therefore, I have to explain and give the formulas. This is how I did it. Let me see whether there is more on the ramp. No. We have 5 minutes past half. Maybe it's before I would proceed with the non-parametric, I would be happy to answer your questions on the ramp, if there are. I look on the chat, but I don't see anything. Certainly, you will be exhausted. This is more than I did in all the courses before. Usually people have, after one course, a lunch, a nice lunch at my office, then we have a joint coffee, and then we have some chats, and then we slowly proceed to the next lecture and so on. Evidently, this can't be done online. What should I do? Should I proceed to the final part? We can already make now a break if you are exhausted. I'm happy with any choice you make.
Maybe we should finish by 2 and stick to the schedule.
Yeah.
I think it would be easier because we have another session going on for early stage researchers. So
yeah.
I will have to run down.
I just wonder whether I should now. I think it's better if I move now to the tutorial, because the tutorial would be on the software for the ramp, which is called Ramp Fits.
Yeah.
Because that would be no new concepts. And then we stop sometimes at 2 o'clock, and then we proceed. And if there is time, then in the afternoon, then I can return to this part, to the non-parametric regression. I think it's better than opening a new Pandora box now.
Oh, that's a good idea.
It's okay?
Yeah, we can finish now by 2, and then on 4 we continue with practical session and your.
Yeah. So I will now go to the tutorial, and I will myself do it on the machine, and I have to also to see how well I am at showing it on the machine, and then you just relax and watch me, and later you have to do it yourself. So let me proceed, and we ignore this stuff, excuse me. And we are now here in the tutorial. And then I just okay, and we deal with the ramp, okay, and now this is a green box. I will now use my sheet of paper. I will now do the exercise, and you see here that I still have computers, but I also have things to write on, because taking notes is, if you do statistical analysis, it is as important as if you have a lab book for your measurements. You should write everything you do, because so easily you make a new thing, a transformation, or removing some data points or something like this. It's very easy to get lost, and therefore my advice is take your notes and invest some time that you are able to understand what you did a month or so ago. So I will now, therefore I write here, the file is 1 minus 2.txt, so this is the data file. Sorry, at the moment it doesn't work. Can you hear me still? I can't hear you as well.
We can hear you, okay.
Okay, now I can hear. I have to see, I will now close this one here. So I'm here, and you see this stuff. And I will, okay. Excuse me, I have, my fault. I have to log in again. I forgot that I should not have done this. Oh, am I here? No. I have to ask again, excuse me, for permission.
I gave the permission for sharing.
Yeah, I have now to see how to do this. I open the...
You can share the complete screen. You have that.
How does it go?
I think it says share screen. It means that it will share that everything is on the screen, not just one program or one file, but everything that is on the screen.
Yeah, okay, I have it, yeah.
Yeah, okay. Now we can see your documents.
Yeah. Okay, I have to. So now, okay, I have to check for the folder. It is in the project, my company, the projects. Where is it here? The training. You see how well ordered my stuff is. Okay, so this is now the book. This is the reading material, where the stuff is, some papers I put in for you. This is the slides, and I will now go to the software. Double click on software, and here is RAMFit, on which I double click in a second. Let me shortly explain the others. I will also study with you another regression model called BreakFit after the lunch. This is a command line window, because you see that now I use the mouse and such things, and I will open the command line in a second, because it is quite convenient, I found out, to work with the keyboard. Okay, sorry, I use a command line for working with the keyboard. And then this is a graphics viewer, another graphics software. This is a non-parametric software, the kernel. This is a powerful text editor, which I also put in for you. And now I will go to the RAMFit folder. I double click here. And this is inside. And this stuff here, this is the editor. These are files for the editor. Where, this stuff here, we don't need to look on this. This is the executable I will run in a second. This is a file name. I will open also in a second. And this is a link to the command line on my Windows machine, which I double click now, so the window opens. And I have to check and perhaps to resize the window. Let me see. Yeah, I want to have it a bit bigger. And increase this stuff here. Oh, where is it? Oh, okay. Yeah, it's a bit strange for me. Okay, I will now I use the keyboard, and I will first edit and open the data file, and I press the tab key to make life easy. And now the text editor opens, and you see this is time. Sorry, it doesn't work here. So this is time, and this is the value, okay? I will just close that file. And now I run the software. Now I press the tab key, it auto-completes. This is because I'm a human and I'm lazy and I want to make life easy. And I press as often as till this stuff is here. So this is ramfit c.exe. This is the coarse version. Maybe, excuse me, I will make this a bit, I give it a larger fonts. I go here, and then I go to layout. First, I will increase this maybe to 110. 110, this is one. And then I make it, oh, maybe I make it a bit bigger. And then so you see how you can tweak your software. Okay, now it's a bit bigger. Then I have to be careful about the size. Okay, so I'm happy now with this. I press now enter and the software runs. You see the link to my famous paper. Well, it's just a paper in Computers and Geosciences. This is a typical journal for publishing softwares for geosciences. It's not a high impact journal, don't worry. So it's 1-2.txt. This is I type in now, okay? Now the GNU plot graphic software opens, okay? We see the plot, okay? In this case, the y-axis is not inverted. I will press enter now, enter. And now we have here the information field, data file name, time interval, number of points. And if some of you are interested in the maximum or minimum or mean values of standard deviation of the x values or the time spacing values, they are here, okay, but we don't need this. Now we are in part 1, what I call detection. We could now extract certain time intervals. I don't do this here. Maybe I do what I call a mean k nearest neighbor, KNN smoothing. I press M and enter. So this stuff here in this parentheses, this is what I can type in. Now I have to type in an integer between 1 and 8 to 1. So let me take 100. So we now take the running mean in a window that contains the 100 nearest neighbor to a time point, so the time neighbors. Okay, and this is hardly visible, so I will try to make this a bit nicer. It depends really on the machines, therefore I have to change this, and I think it's line number 3. I have to check. It's a bit tricky. I think it's this stuff here, and I give this a bigger value. I hope that it's, yeah. Okay. So this green line is now this running k nearest neighbor mean. And here we have bigger values, and here we have smaller. I press enter to proceed. And now I press Z to continue. And now we are in part 2, the regression. And let us start with OLS. That means the prescribed standard deviation is set constant, no weighting. Later in the tutorial, we will explore other options, namely to employ a ramp form for the variability. The ramp parameters would be then T1S. This is a 1 change point time for the variability. The level would be S1, okay, and then this would be another. But now I will just press Z to employ a constant weighting of unity. You can put in any number but 0, because you should not divide by 0. I use 1. Okay, now I told you about my wonderful computers and that they are fast in nanoseconds or microseconds, but now we are dealing with ramp estimation and brute force search. That means we try many candidates for change point times, and we want to shorten down the search. And therefore, we narrow the search ranges in which we look for T1 and T2. And we learned that T1, this is the smaller value, it was at around 2,400. The units are kilo years. And the earlier one was at around 3,700. That means I do search for T1 not between 1999 and 4001, but only between 1999 and let us take 2950. And for T2 we search maybe between 350 and 4001. So we narrow down the search range. That means we reduce the computational burden. This was still pretty fast. Let me show you. I will now again make this line style a bit nicer. I want to give it a 4. It's a bit thicker. No, this one was the wrong one. I have to check where it is. It is a red one again. Yeah, I can't remember this stuff, therefore I have to do it. I'm a bit puzzled. Why does it not? This should work. No, I have no idea why it doesn't work. Anyhow, I think you are still able to see these change points here. And also you should see the vertical bars. This one here, the other is hidden behind the border. This is a search range for T1. And this here from 3050 to the maximum is the search range for T2. And you see that these search ranges nicely, I hope this expression is okay, bracket the found minimum here, the optimum. There's a lot of space here and a lot of space there. If our search range would be here, then the solution would sit close to the boundary. This would be then dangerous for the simulations, because some of the simulations will have a simulated change point then in excess, maybe here. Therefore, the search bounds should be wide enough to allow for some uncertainty. I will press now Enter and look on the standard deviation, which we ignore, and continue. And now we look on the residuals. Data minus fits divided by variability divided by 1, that means data minus fits. A histogram. In fact, this is very close to the histogram in the book because it's the same data set. We have perhaps a mild form of right skewness here. Okay? This plot is called normal probability plot. On the horizontal axis, you see the size sorted residuals. So this one here would be the smallest, and this is the largest one. And the normally an empirical distribution would have a value here of 0, then 1, 2, 3, and unit steps. But here, for this plot, this scale, the y-scale, is transformed such that a Gaussian distribution would yield a straight line. This is called a normal probability plot. And indeed, the line is very close to a straight one. Only here in the upper parts you see some deviations. Only mild forms of skewness. So let me proceed. This is residuals against time, and here you would have a glimpse that here the variation is a bit smaller compared to there. Okay? Therefore, in the tutorial after the lunch, we will do a weighting to take that into account. This is a leg 1 scatter plot. In this case, I plotted R of I, the current one, against the preceding one here. Anyhow, you have an orientation here, and we proceed. I will continue now and the remaining thing is then done with the Bootstrap. Now we do the error bars. It may well be that we extend now between 14 o'clock, I have no idea. This is a Karlstein formula for block length. I don't change this, n. Let me just take a 100 simulations. So it's, you see that the counter runs. Okay, the machine is, I bought it new. It's faster than the old one. And this is then the result. These are the numbers I look at. This is the uncertainty, the standard error for the fitted change point. Okay? This is the uncertainty for the other one. So now we have the result. And you notice also, and this will be close to the end of what I say, you can also quantify the linear part between the change points. And later, you will learn that you can use ramfit also for linear regression. Then you would narrow down the search range. The first change point 1 would be the first time point, and the other change point time would be the last time point. And in between, you would then just look on the straight line in between. And then you have the slope, this standard error, and the intercept, this standard error. The advantage of that software is that it is applicable also for non-Gaussian shapes and for persistence. Situations your regression software, linear regression software, likely is not able to do. So I will now come to an end. I press Z to continue. You could go now back to previous steps in the software. This is the usual way, interactive working. Now we have lunch. I press X and enter, and we see then the output files that have been written. Okay? And this would be then the things you take home, you write your thesis from, and to write your paper from. But be aware, if you rerun the software, it will overwrite your output files. So in between, you have to, well, save and copy your output files. So with great pleasure, I had you here for these 3 hours. It was also for me a kind of experience. And I hear your questions with great pleasure. And I would be then back at 14 o'clock. Thanks a lot.